What's going on, everybody? Welcome back. Patrick here, and we're going to do another rate of change question. So we have to find the instantaneous rate of change of f of x equals square root of 3x plus 4 at this x value negative 1 using the squeeze method. Now the squeeze method, it basically is another word for the centered interval method. So what we have to do is we have to take the x value for which we are finding the instantaneous rate of change at, and then find an x value that's close to it on both the left side and the right side, and they have the same distance. So let's say we pick an x value like negative 1.1. Well, that would give us an x value negative 0.9, right? So 0.1 distance to each side. And now what you do, since these x values are very close to this x value that we are working with, you find the average rate of change for this interval here. So if we use this interval, the average rate of change in this interval would be, It would be f of negative 1.1 minus f of negative 0.9 all over negative 1.1 minus negative 0.9. And to find this f of negative 1.1, what you do is you plug in negative 1.1 for the x in the function, and then you put that value there. So when you input everything in the calculator, f of negative 1.1, if you plug in negative 1.1 for the x value, you would get 0.83666 minus f of negative 0.9. If you plug in negative 0.9 for the x value, you would get 1.14017. And that's going to be all over negative 0.2, because negative 1.1 subtract negative 0.9, these would turn into a positive. You would end up getting negative 0.2 in the denominator. And when you do that in your calculator, you would get 1.51755. So that is one approximation. But usually what the squeeze method requires is that you continue to pick intervals that are closer and closer to that x value you're working with, in this case, this negative 1. So some teachers may allow you to just finish here and then give you this as the final answer. Other teachers want another tighter interval. You want to keep squeezing the interval. So what I mean by that is, let me erase this here. So let's write negative 1 again, and now let's pick a tighter interval. Let's squeeze the interval a little bit more. So picking a number to the left that's very close to negative 1, that's closer than negative 1.1, would be something like negative 1.01. And then on the right side, negative 0.99. Right? So now, instead of 0.1 being on both sides, we now have 0.01 being subtracted and added to negative 1 to get a even tighter interval. We're squeezing the interval. And then what we do is we find the average rate of change between these two new x values. So same thing. We would just find f of negative 1.01, subtract f of negative 0.99, all over negative 1.01 minus negative 0.99. And same thing, to find f of negative 1.01, we would take negative 1.01, plug it for the x value in the function, and then put that decimal there. So if you plug all of that in, f of negative 1.01 would be 0.98486. f of negative 0.99, if you plug in negative 0.99 for the x value in the function, you would end up getting 1.014889. That's going to be divided by negative 0.02, which is what the denominator simplifies to. And then when you simplify this whole expression in your calculator, you would end up getting 1.50015. So notice that the tighter of an interval we are using, it's approaching this value of 1.5. You can repeat this process again with an even tighter interval, so you can use like negative 1.001 and negative 0.999. And if you use those numbers and follow the same process, you will see this rate of change approaching this value of 1.5. So from all of this, we can be pretty confident that the instantaneous rate of change of this function at an x value -1 is 1.5. That is your answer. Now again, some teachers may want you to use multiple intervals, so you start with a fairly wide interval, so 0.1 on both sides, so -1.1, -0.9, and then you can use tighter and tighter intervals. You're squeezing that interval, so like -1.01, -0.99, and then you could even use a third one, as I mentioned before. But whatever you do, the tighter you squeeze those intervals, you'll see that the instantaneous rate of change using the centered interval method is approaching this value of 1.5. That's your final answer.